Welcome everyone. Today we're going to be talking about, we're going to be in fact starting a series of lectures on deployments of differential privacy. And today's will focus on deployments in particular of local differential privacy. I was considering originally making two different lectures on this, one which was first on the theory of local differential privacy, and then another one on deployments, but we're kind of running low on time in the semester, so I'll just do one. I wanted to combine them, and I'll just talk about LDP viewed through the lens of deployments in DP. And along the way, I'll mention a few of the highlights which are both interesting, both in practice as well as in theory. Okay, but before we go any further, let's talk about what local differential privacy actually is and how it differs from the standard model of differential privacy that we've looked at so far. So the standard model of differential privacy has had something like the following type of picture, where we have, data over here, then there's the curator over here. And the idea is they all send their data to the curator. And then the idea is that right here, there is the public. And in the standard trusted curator or central DP model, the privacy barrier is right here. What does that mean? It means that, we picture that the adversary is standing over here on this side of the curator, on this side of the curator. Basically, anything that the curator outputs is visible to the adversary. So while everything behind on this side is trusted, everything on this side of the curator is untrusted. In particular, this means that the users, who are sort of represented as holding x1 through xn, they can send their data in the clear to the curator with no sort of privatization, because they trust the curator. So this is sort of what's known as the central model. On the other hand, we can imagine a more challenging privacy setting where the trust model, or the trust barrier, the privacy barrier, is moved way over here. Instead of making me draw this little gentleman again, let's just put him over here now. And so this is what is known as the local model. Okay, it's orange. The idea here is that maybe there is no trusted curator. You don't trust anyone. For example, let's see the example that I mentioned at the beginning of this class, where there's an instructor for a class and they want to discover what fraction of their class cheated on a test. The curator for this case would be potentially the teacher, the instructor for the class. But of course, students would not be willing to reveal their private information as to whether they cheated or not. They probably wouldn't want to reveal that information to anyone. So in other words, every user is going to have to privatize their own data point before, in some way, whatever they reveal to the anyone else will be privatized in the same differential privacy definition we've used before. So yeah, it moves, essentially the local model moves the trust barrier to be closer to the users. And so it can be seen as a stronger notion of data privacy, and this has benefits, like it's a stronger threat model. You're safe against more types of adversaries which might show up, but on the downside, you're going to get worse error. And let's see exactly how this might come up. So let's revisit the example we studied way at the beginning of this class. And we want to estimate the mean. So we have x1 through xn, which is some arbitrary data set, and we want to estimate mu equals the average of these bits. Let's say also that these are in 0, 1 to the n. And we want to estimate mu, which is equal to the average of these bits. So in the central model of differential privacy, what we would do is just simply compute the empirical mean and noise it. Mu hat equals 1 over n xi plus Laplace of 1 over epsilon n. So yeah, we've studied this a million times, but this is going to be differentially private just using the Laplace mechanism. And the important thing to notice is that the noise that we introduce due to privacy is going to be of order 1 over epsilon n. So we have that mu hat minus mu is going to be less than or equal to, say, ignoring constant factors, I'm just going to leave those out, 1 over epsilon n. Okay, so another way of saying this is if we want accuracy to be less than or equal to, or the error to be less than or equal to alpha, then we need n to be greater than or equal to 1 over alpha epsilon. Good, so that's nice and easy. This is a central differential privacy. But what about local differential privacy? In particular, let's recall randomized response. This is sort of the first differentially private algorithm we studied at the very beginning of this class. And this is defined as follows. The user I will output a bit yi, which is equal to xi with probability e to the epsilon over 1 plus e to the epsilon. And then it's equal to 1 minus xi with probability 1 over 1 plus e to the epsilon. Notice that this is a little bit different from how we defined it at the beginning. At the beginning, we defined it roughly something like 1/2 plus gamma and 1/2 minus gamma, where it would tell the truth with probability, 1/2 plus gamma, and flip it with probability 1/2 minus gamma. But this can be roughly seen as the same because, as we're doing here, just because of the fact that this is approximately equal to, when epsilon is small at least, 1 plus epsilon over 2 plus epsilon. And so it's kind of close enough to that. But that's just an aside if you have a very good memory from the beginning of this class. So yeah, this is what the user does. But we haven't said what, so what the user does is they take their initial, bit, whatever it is, 0 or 1, and they flip it or randomly flip it potentially with these probabilities to generate a new bit yi, which is either 0 or 1. So this is epsilon dp. Why is that? It's not too hard to see, just because if their data point is changed from a 0 to 1, then the ratio will be of seeing a particular outcome will be essentially just the ratio of these two. It'll be like e to the epsilon divided by 1 plus e to the epsilon divided by 1 over 1 plus e to the epsilon, which is like e to the epsilon. So we can see that there's a fairly, this is exactly differentially private in the definition that we've used before. Okay, so that shows that it's differentially private. Now, so they can send out these messages, and that'll be totally differentially private for everyone. But the question is, how accurate will this be? And we haven't even gotten to the point of how accurate it'll be. The first thing that we should ask is, what does the curator actually do? And the curator, I claim, will do something like the following. They will compute mu hat, which is equal to the following rather odd quantity. I'm just going to write it, and then maybe we'll sort of see why it is. They are going to compute this value based on the responses. Why is this? Well, let's see if we can actually do the computations. Like, what we want to do is essentially show that this value here, that the expectation of essentially whatever we have in here is equal to xi. So let's sort of do that. Expectation of mu hat is equal to let me just write this here, 1 over n summation expectation, just by linearity of expectations, we have this. And what we can do is essentially just expand out the expression for the expectation of yi. This equals 1 over n. And here we have, this will be xi times e to the epsilon over 1 plus e to the epsilon plus 1 minus xi times 1 over 1 plus e to the epsilon, and then minus 1 over e to the epsilon minus 1. Now, this will cancel with these two terms right here. And so this will just go in the numerator there. Let's continue writing this out. We have, let's see what's the best way to simplify this. So we have, I'll just write it out without, well, let's pull this 1 out. This is going to be a plus 1 over e to the epsilon minus 1. And using this here, that'll be minus 1 over e to the epsilon minus 1. So these two sort of cancel each other out. And now we're left with, let's just write it, xi times e to the epsilon minus xi over e to the epsilon minus 1. And you can see that this sort of factoring out the xi, this becomes equal to 1 over n summation of xi, which is equal to mu, which is the mean. Okay, so it was quite a bit of work, but we finally got there. Yeah, so this is of order. This is an unbiased. In other words, if the curator computes this value here, they'll get that it's an unbiased estimator for the true mean, which is, yeah, this. Also simple calculations show that the variance, yeah, really, it's not too hard to see that the variance of this quantity is going to be of what it's going to be. Well, yeah, let's do this calculation as well, in fact. So the variance of mu hat. I'm going to only do this very roughly, but the variance of this is going to be something like, essentially you can pull out these constants because they're not going to affect the variance. Like, okay, I'll write it like the following. First of all, you can get rid of this additive term here because that's a constant. So the variance is going to be the variance of 1 over n summation of this term here. So let me just write this term very roughly using the sort of typical e to the epsilon, using the approximation that e to the epsilon is approximately 1 plus epsilon, which is a true approximation for small values of epsilon. So this gives us roughly that the numerator is 2 plus epsilon divided by epsilon times yi. And so this we can expand as follows. So there's a few simple rules for variance, which one is that if you have a constant, it'll be squared. The other thing is if you have a summation of independent, random variables, then the variances will add. Therefore, we can sort of pull this out and say that this is going to be equal to 1 over n squared times, that's just pulling out this constant, times n, because it's a summation over n things, which are independent, times 2 plus epsilon over epsilon squared times variance of yi. And the great thing is because yi is a Bernoulli random variable, its variance is less than or equal to 1/4. Yeah, this isn't too hard to see. It's kind of a simple fact because of the variance of Bernoulli. But let's just write this as this is equal to, say, order of 1 over n times epsilon squared. So, okay, we have now a fact that this is an unbiased estimator, and we have a bound on the variance. So simply using that, using Chebyshev's inequality, we can say that with high probability, we have mu hat, the estimate of the mean, minus mu, is going to be less than or equal to roughly, ignoring constants as usual, epsilon times square root n. Yeah, so, and another way of saying this again is if we wish to bound mu hat minus mu less than alpha requires n to be greater than or equal to 1 over alpha epsilon squared on both terms. Okay, so this is the let's recall what we just proved. We just did a lot of work, but let's see what we proved. So now we have two sort of bounds on different estimators in terms of how much error we get and how much data we need. So this is the central DP, and this is the LDP guarantee. So we can say that central DP, like we said, it's a weaker trust model, but it requires much less data, whereas LDP requires it's a stronger threat model rather, and but it requires more data to get the same error, quadratically more data. So that there's kind of a trade-off here depending on which type of threat model is appropriate for your setting and how much data you have. For example, if you don't have a lot of data, then it's typically the case that LDP will be absolutely terrible in terms of accuracy. So you just can't hope to do anything meaningful there. Yeah, this is going to be key for our investigation today because in particular, all the deployments we're going to talk about today are with respect to companies which have very large amounts of data. That is Google, Apple, and Microsoft, all of which have huge amounts of user data, so they can use local differentially private algorithms which actually give meaningful results. If you have a startup, I wouldn't recommend trying to use local differential privacy on your low user base. Okay, so yeah, we'll go into those in a second. Let me just mention that there's I think there's a lot of very interesting technical questions and sort of theoretical questions which involve local differential privacy, which are very fascinating, perhaps are some of the most interesting open questions in terms of theory in the world of differential privacy. One question is the role of the role of interactivity. How does it affect the power of local differential privacy? So, just to sort of tell you what I mean by that, you can imagine there's sort of different types of interactions between the curator and the users. So in the sort of, I'm going to copy this 3 times because we're going to use it a few times. So let me just sort of illustrate this as we go. So in the non-interactive, we have just everyone just sends one message, which is appropriately privatized to the curator, all at sort of the same time. They send whatever their thing is. And yeah, that's that. So that's sort of what you might, this might be what you usually think of, what you might think of would happen in the setting. But there's actually other things which could happen as well. For example, there's what's known as the sequentially interactive setting, where in this case, we can have a sort of sequence of interactions. For example, maybe first user 1 sends a privatization of their data, and then the curator, based on this, will ask a new query to user 2. And based on whatever this query that was sent, then the user will send potentially a different type of privatization. They might run a totally different differentially private function on their data point and send a new privatization of that point. And then we go on to the next one. Q3 is sort of asked to the third user, and they could send a different privatization as well. Like, yeah, maybe the first person runs randomized response, the second person they choose to run the Laplace mechanism, just something that is potentially different and perhaps depends on this query that was asked. So this is a sequentially interactive model. The sort of thing that makes it sequentially interactive is the fact that once a curator asks a user something, then they can't ask that user something again. So you kind of have to go in sequence. And then there's the fully interactive model, or just the interactive model, where all bets are off. For example, user 1 and can send some privatization, then the curator can go say to user 2, and then they get something from user 2, and then maybe they go back to user 1 and ask, and they get something, and then they get something interesting, so they go back to user 1 again, and then user 1 sends something back, and then maybe now user 3 sends something at this point, and you get the idea. There's no real restrictions as to what sort of order things can be asked in. So the role of interactivity is still a very interesting question. I would say is not fully understood, though there's been some nice advances in the last couple of years in terms of getting an understanding. But yeah, there's still some interesting questions going on here. And there's still some mysteries. So another interesting thing is the fact that in this class, we're seeing a lot of very strong separations between pure and approximate differential privacy, in the sense that, there's something that you can do in approximate differential privacy that would never work in pure differential privacy. For example, things like proposed test release. That's sort of an inherently approximate differentially private type of question. So, but that said, at least in the local differentially private setting, to the best of my knowledge, I don't think there's any place we know of real separations between these two models. And in fact, in certain types of settings, it's known that they're actually equivalent, that any approximate DP algorithm can be converted to a pure differentially private algorithm. For example, I think in the any sequentially interactive protocol might be able to be converted to a pure locally differentially private sequentially interactive protocol. So yeah, these are all a bunch of very interesting technical questions, but unfortunately we don't have time to discuss them too much in this course, at least. But yeah, there's something, if you're looking for some very interesting technical questions, these are some types of things you can try to investigate. Okay, and in terms of like just a little bit of a history lesson, where did local differential privacy come from? Well, first and very classically, it was introduced even before differential privacy was invented or discovered, however you want to call it. The first paper was by randomized response by Warner in 1965. Very old paper, but he essentially came up with this randomized response algorithm. Perhaps more recently, there was another one again, which was also before differential privacy, by Efimievsky, Gerke, and Shrikant. And this was in 2003. And the one which I think is often considered to be when like local differential privacy was actually formalized is a paper by Kasi Viswanathan, Lee Nisim, Raskodnikova, and Smith. This is obviously quite, and this is a paper from, I guess, 2008, first of all. This is quite a long name, so it's sometimes affectionately known as the Cleaners paper. Another important paper in this sort of line is one by Ducci, Jordan, and Wainwright in 2013, much later. This is sometimes credited with, it's sometimes credited with popularizing the notion of local differential privacy in certain communities and investigating some of the important statistical properties of in a differentially private setting. So yeah, that's it for the setup and sort of like an overview of LDP. Let's start talking about different deployments. And the first one we'll talk about is the deployment of differential privacy at Google, which is perhaps the first large-scale deployment of differential privacy at, say, a tech company. And we're going to be talking about a system known as Rapport. And this was in a paper by Erlingson, Ihur, and Orlova in 2014. So yeah, let's describe one of the important use cases and a type of problem that the Rapport system attempts to get around. Let's go back again to the cheating on a test example. Suppose we're in the same situation before. We're trying to find out how many people cheat on a test and ask them to privately report their bit as to whether they cheated or not. So if you just ask everyone once, this is fine. They can use local differential privacy. They can use randomized response and attack. And they can respond, and you get some estimate where you have an idea of how many people in the class cheated or not. Now, this is great for if you just want to do it for one day, but what if you do this again every day? Like you ask, okay, did you cheat on test 1? You ask them on March 3rd, then you ask them on March 4th, did you cheat on test 1? And then you ask the same thing again and again. And you'll realize that if you do this many, many times, then the privacy factor will decay very quickly, and it'll be susceptible to what's known as an averaging attack. So let's be really concrete. Suppose you set epsilon is equal to ln of 3. This is just for simplicity, which means that the randomized response is sort of equivalent to the following. You just say truth with probability 3/4 and lie with probability 1/4. So suppose this is kind of your this is your algorithm when you set epsilon to be ln of 3. So in this case, if the answer the answer came up as yes, suppose RR equals yes, then this implies that this comes up with this is with probability only 1/4 if the user was lying. If the user's value is no. So what am I trying to say here? If it comes up yes, then there's still a pretty reasonable, plausible deniability. Even if it's no. This would 1/4 event still happens fairly often. On the other hand, if you do 100 days in a row, and you see, RR equals 75 yeses and 25 no's, then this only happens with probability 1.39 times 10 to the minus 24 if the value is no. So all I'm trying to get across here is the fact that in a single day, if you see a particular outcome, then there's a pretty strong plausible deniability. On the other hand, there's much less plausible deniability in the case when you have several disclosures in a row. And why did this happen? Why did we get such a terrible number here? Like, why did we have such a little plausible deniability? And this is essentially due to, you know, epsilon, due to composition of local differential privacy. Yeah, remember that epsilon is equal to ln of 3, which is approximately equal to 1.1. Well, then this implies that 100 epsilon, due to doing 100 randomized responses, this is approximately equal to 110, thus giving a privacy guarantee of, like, you know, a multiplicative guarantee between the probabilities that the ratio is bounded by e to the 110, which is quite a large number. So yeah, you can see that answering the same question repeatedly or many times in a row can potentially give you terrible privacy. And what's the solution to this? Well, the solution might be kind of obvious to you for the setting. Essentially, just don't keep flipping coins each day. Once you answer a question, just keep repeating that same answer every time you're asked a question. So this is a strategy that is known as memoization. Not to be confused with memorization. It's kind of a similar principle, but it's called memoization. Yeah, and then every time the user is asked a query, they basically see, have I answered this query or not privately? If they have already answered the query privately, then they output the same randomization they computed before. If they do not have a, if they haven't done it before, then they just have to recompute it. So essentially, they'll just do a randomized response on day 1 and then repeat that value every subsequent day. And the adversary cannot learn anything new from these subsequent disclosures because it's the exact same value that we've seen before. So this isn't, so basically, let me just summarize what memoization is. It says, you know, don't re-randomize the same query. Don't re-randomize your answer to the same query. Yeah, this is not a foolproof system. For example, the adversary could ask the same question semantically in sort of slightly different ways. Just to give you kind of a simple example, suppose they ask you, first of all, you know, what's your PIN? And then they also ask you the like your PIN to your bank account. And then they could also ask you, what is your PIN reversed or permuted? You know, if they ask you for your PIN and your PIN in reverse, then these are kind of, you know, the very similar types of queries. So they can sort of trick you in these ways into answering the same query multiple times and therefore weakening your privacy guarantee because if you re-randomize. But it can work in a system when the user or the system is trying to honestly preserve user privacy, just asking the same query in subsequent days, stuff like that. So yeah, this is kind of one of the key things that a company you might imagine is trying to do when doing telemetry, or like basically trying to understand user signals. They'd want to, because they want to find out what the user has been doing in the last day, every day. They want to make sure that they don't really, you know, they don't ask the user the same sort of question many times because maybe a lot of the time, it won't have changed. Yeah. So there's an illustration of the system right here. Let me just move this upwards, I guess. Yeah, so this is sort of a figure as to how Rapport works. And there's a lot going on here, so don't worry, we'll go through it step by step. But the first thing we're going to do is, well, the first thing I'll comment is the fact that this works in a more general setting than randomized response. Remember that randomized response was equal to, had the values equal to like 0 or 1. The domain was 0, 1 variables. But here we're going to be able to handle arbitrary kinds of values within a set. So for this, for Rapport, we're going to have, a user will have a value v, which is in some domain x, and then it'll map to a length k binary vector. And this we'll call it b. And this is using what's known as a Bloom filter. So if you don't know what Bloom filters are, don't worry about it too much. I guess a brief sort of summary of it will be saying that you take whatever value is here. Oh, okay. So let me say it like this: you select a number of different hash functions, say like h different hash functions, which map from the domain x to the set of numbers 1 through k, done uniformly at random. And what you do is you apply, you set b to be equal to 1 if one of the hash functions map to that entry. So let me say, let's say these hash functions are h1 all the way through hh. Sorry, this is not great notation. Let's say these hash functions are f1 through fh. So then, yeah, given this, then we'll do the following. We'll set bj is equal to 1 if say there exists I such that fi of v is equal to j. Okay, this is a really verbose way of saying it, but basically all it says is that you set the Bloom filter, you set this vector to be a 1 exactly when a hash function maps it to those values and 0 otherwise. So for example, this was the value, you feed it into a hash function and that hash function maps it to here. So you set that bit equal to 1. And then that hash function also maps, a different hash function maps this value over here. So you set that also to be 1. Another one maps it over here. That's also equal to 1. And this one maps it here. So that's also equal to 1. And everything else is going to be 0. So that is what a Bloom filter essentially does. Yeah. So a simple case is when h equals 1, for example. This is kind of maybe the one you should think of, keep in mind, just for simplicity. It's saying that this would be equivalent to doing a one-hot encoding of the input domain. So yeah, it takes sort of an arbitrary value and it maps it to a vector, which is 1 exactly one location and 0 everywhere else. So that is kind of the first step of the Rapport system. Nothing has really happened yet. It really just took whatever sort of arbitrary domain and converted to a binary vector, which is which is a more convenient representation for the type of operations we're going to perform. So the first step, given this sort of representation, no privatization has happened yet. The first step to do is what's known as the permanent randomized response. So from going to this Bloom filter B, we'll go to a fake Bloom filter B prime using what's known as using the permanent randomized response. And yeah, essentially what we're saying here is that this is going to be something that we essentially memoize. We're going to sort of remember this, but what exactly is it? Well, all we do is take this Bloom filter and or the sort of the vector b, and what we do is from there we do apply a bitwise randomized response mechanism. So essentially each bit will be just run through a standard randomized response using appropriate privacy parameters such that the result b prime is going to be locally differentially private. So yeah, and in fact you can consider this to be like kind of done at this point, if in the sense that don't worry too much about this yet. We'll come into that. But essentially, now every time the user is asked for, you know, what is their value, then they can simply output this fake Bloom filter value b prime right here. Yeah, that'll go out, and they can the sort of adversary, or rather the curator, can just take a look at b prime, all the b primes from different users, and aggregate them in an appropriate way. And that's totally differentially private. They'll memoize this b prime so that they don't have to recompute every time. So now you might be wondering, why is this report sent to server kind of different? There is one more step which Rapport takes an additional precaution. Like, this is going to be locally differentially private. So in terms of LD, in sort of the threat model that we generally consider in local differential privacy, it's fine to just keep outputting b prime whenever it's asked. However, there might be some situations where just outputting b prime is somehow an identifier. So consider, you know, you ask a user some question and they return this vector. This is a pretty rare vector in the sense that, you know, this is, I guess, 256 bits, and there's 2 to the 256 possible bit strings they could see, that the curator could see. But this particular one came up, and this was sort of chosen randomly. So if this one comes up once and it comes up again, then it seems pretty likely every time that this one comes up that this is going to be corresponding to the same user. So this gives you some sort of things like timing attacks. You can tell based on when you receive this message which user it is, even though ideally you'd like it to be sort of de-identifying and detached from the user who is you know, asking these questions, or who is answering these questions. So in order to get rid of and deal with these types of issues, they have an additional randomization step. So this is a little bit of an ad hoc method, but it still works pretty well in practice, and it does indeed try to, you know, block these other types of attacks, which are in an even stronger model than local differential privacy, where we care about when the adversary is seeing which messages come out of which people, and trying to use that as sort of additional information. So it's just a very simple protocol to go from b prime to the actual report sent to the server. They just sort of flip every single bit with probability, say, or I guess the way they do it, these are parameters, but the parameters they said in the paper say, if a bit is equal to 1, then we will just we'll just like preserve that bit with probability 0.75 and flip it otherwise. And I think the clear bits, the ones which are 0, they're just flipped 50-50. So this gives you another layer of protection using this bitwise randomized response, while still, what does this do? This gives you actually a little bit more local differential privacy if you just do one report. But this actually has an additional sort of, even if the user sends many different reports and they send many of these different sort of randomized strings, which are you know, very random and private looking, even if they send many of them and the sort of adversary manages to figure out the pattern and figure out, oh, all of these strings that we sent here were sent by the same user, because it sort of corresponds to this fake Bloom filter b prime. Even if they manage to crack sort of the true b prime that's underlying these, well, they're still okay, I claim, just because of the fact that you know, this is a permanent randomized response, meaning that no matter what, we'll always fall back on the local privacy guarantees of b prime. Right, so in sort of summary, there's sort of a permanent guarantee of privacy based on the fact that they memoize and never reveal anything more than just b prime. But then there's another layer on top of it, which is just sort of other, somewhat ad hoc, but also useful privacy in other settings. So yeah, this is how I've only described how this very sort of kind of comparatively complicated procedure, at least complicated compared to say randomized response, which is very simple. I've described this complicated procedure, and there's a kind of also complicated way of decoding these messages. For example, if the user receives several of these reports, how do they actually go from that to finding out the true values, which is what the curator cares about. So there's a system for that, but I'm not going to get into it too much. It's kind of just more like a more sophisticated way of doing the randomized response decoding. But you can check out the paper if you care. One interesting case is that it can't handle, that we'll reveal or we'll discuss later on, is when values that the users are asked to report do differ, but they differ in a very sort of small way, which maybe we would hope could still be privatized. So for example, like this handled the case, imagine the curator asked the user, what's your favorite number? And then they say the number 68. And so they ask them every day, what's your favorite number? And they keep their favorite number, the number 68. But it can't handle cases where the user's data might actually change, but say change by a little bit. So for example, if I kind of mentioned this before, this is a silly example because there's a way that the user could get around it. But suppose the user was asked, what's your favorite number? They say 68, and then they're asked, what's your favorite number plus 1? And then they would have to sort of do a new randomized response and answer 69, and that would be a loss of privacy. So they can't really handle the case where the values change, but only a little bit. To give you one more concrete example, suppose that there was a query just asking a user every day, what is your age in days? And so first, I don't know, in the first day it would be maybe 10,000, and then the next day it would be 10,001, and then 10,002, and then a new rapport for each of these would have to be generated, and everyone would lose a factor of epsilon in terms of the privacy budget. So this would be bad as you start asking more and more queries. So Rapport can't really handle this case. We'll talk about another solution by folks at Microsoft, which has a way of handling this type of query, which is sort of relevant to their use cases. But yeah, just to conclude this segment and this part of the lecture, let me just tell you about what did they actually use Rapport for. What was it used for? Well, it was used within the web browser Chrome in order to monitor various aggregate statistics of users. You want to find out what fraction of your users who use Chrome have various settings and stuff like that. The Rapport was used for that. And in particular, it's used for one thing that was used was for malware detection, or kind of trying to understand the behavior of malware. For example, a common type of malware attack is when the user's system is hijacked and certain settings are changed. For example, it could change a user's homepage in their browser to be some sort of advertising page which loads an ad, or is just somehow a bad website for whatever reason. So what they did was they used Rapport, where an opt-in feature, there was an opt-in feature in Chrome which utilized Rapport to privately report homepages, in particular trying to find out what fraction of Google users, Google Chrome users had different homepages. And so there were the usual ones that you might expect. For example, a lot of people probably have surprised Google as a homepage, or maybe Facebook or other websites like that. But they actually were able to detect which websites were frequent, websites that people had their homepages to, which are generally considered malicious. And so this was a technique they could use to try to identify and potentially mitigate effects of malware in these ways. Another example that they use is also, I guess, malware related, but process names. They showed a sort of example using trying to find out privately what processes are running on a certain Windows user's computer. And given this, can you privately discover what processes they're running and try to find out if they have any, say, viruses or spyware running on their computer, or what fraction of users have some sort of spy running on their computer. So this is kind of cool because, like, let me sort of take a big picture. Why do we actually want? Why would we want as Google to be able to use this type of privacy, or this type of local differential privacy? It's because there's some statistics which would be very valuable to us to collect in order to improve the user experience. Things like, controlling malware, or helping to fight these things. On the other hand, users might not be willing to reveal this information because it's kind of sensitive. Maybe you wouldn't want to reveal your home pages about My Little Ponies or something. So therefore, this is a way to respect users' privacy in this regard, while simultaneously getting this information, which is important to make the user experience better. So these are just a couple of examples. So this concludes this part of the lecture. In the next half, we'll talk about deployments, including those by Apple as well as Microsoft.